Hi everybody, welcome back to the Feynman Technique. This is going to be an explanation of the free response question number 3 on the 1999 AP Calculus AB exam. I'm going to be starting a new format doing this. I'm not actually going to be writing the problems out on the board because the the link to the problem is going to be provided in the description of every video. So just click that link and pull up the problem to follow along. What I am going to be doing is writing down the concepts necessary to solve the problems. I think that'll be much more helpful for people trying to study for the AP test. Okay, so this is question number 3 on the free response portion of the test. It says that the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. The table above, and then there's a table there, it's not listed here, shows the rate as measured every 3 hours for a 24-hour period. Okay, so Part A of this question says use a midpoint Riemann sum with 4 subdivisions of equal length to approximate the integral from 0 to 24 of r of t, which is the rate of water that flows out of the pipe. Using correct units, explain the meaning of your answer in terms of water flow. Okay, so there's going to be 2 concepts that I have listed here used in this portion of the problem. The first one is the midpoint Riemann sum, and the second one is this. We'll start with the midpoint Riemann sum. So I hope you all know what a Riemann sum is. If you're studying for the AP Calculus exam, you probably should know what it is, but I'm going to go over it really quick. It's an approximation to a definite integral. This particular Riemann sum that I have up here approximates the value going from 0 to 8. And what a midpoint Riemann sum does is, well, first you divide it up into intervals. They don't have to be of equal length. In this case, they are. And then what you do is, for each interval, you take the midpoint and you travel upwards till you get to the point. Well, let's say if this is the function f of x, you would have x here, and this your x would be the midpoint between your interval. This one going from 0 to 2, so the midpoint would be 1. So you have 1, you go to the point 1, f of 1, which is basically just making a vertical line up until it touches the graph of the function. And then you make a horizontal line going over to the end of your interval and to the beginning of the interval, and you draw a rectangle, and that's your first rectangle. And then you do the same thing. So you can see we go going from 0 to 2, the midpoint is 1. We travel up there, go over, draw a rectangle. Our second interval is from 2 to 4. So the midpoint is 3. We take f of 3, go over. Midpoint between 4 and 6 is 5, up, over. Midpoint between 6 and 8 is 7, up, over, and down, just like that. So to use that on our problem, well, if you're looking at the chart, it lists T in hours and R of T in gallons per hour. And it says to divide it into 4 subdivisions. Well, our t is going from 0 to 24, so dividing that into 4 subdivisions would be a length of 6. And they're all of equal length. So the midpoint, so if we had the interval 0 to 6, 6 to 12, 12 to 18, and 18 to 24, our midpoints would be 3, 9, 15, and 21. So basically all we have to do is we are adding up a bunch of rectangles with a bunch of rectangles that are like this. And this represents the length of our rectangle, and this represents the width. So our length in this case is always 6 because we're dividing 24 up into 4 separate subdivisions. And then the height is just going to be the midpoint between, the midpoint of our intervals. Our first interval is 0 to 6. So the midpoint of that is 3, and luckily in the chart it gives you that value. It is 10.4. And then we're going to have, so we have 6 times 10.4 as our first rectangle. What's our second rectangle? Well, it is, our second subinterval is from 6 to 12. So it's also a length of 6. And the midpoint between 6 and 12 is 9, and it gives that to us. At 9 hours, the rate is 11.2. So we would have plus 6 times 11.2. And you'll notice that every single one of these intervals is going to be, sub-intervals is going to be of length 6. So we can just do 6, and then literally pull the values right out of our chart. The first value is 10.4. Our second one is 11.2. Our third one, which corresponds to the midpoint between 12 and 18, which is 15, is 11.3. Let me double check this. Yeah, 0.2, yeah, 10.4. Yeah. And then our fourth one is the midpoint between 18 and 24, which is 21, and that value is 10.2. So, if we add all these things up and multiply by 6, what we get is 258.6. Yeah, that's what we get. And then it says, explain the meaning of your answer in terms of water flow. Okay, well, this is where we have to pull out the second concept here. And this is very abbreviated. This is just kind of like something to keep in mind. In general, the integral from some start to some finish, in our case, our start is 0 in terms of time, and our finish is 24 in terms of time. But anyway, the integral from start to finish of some rate, usually, in this case, our rate is r of t, and it describes the rate at which water flows out of the pipe. So the integral from start to finish of rate is the total. If you integrate a rate over an interval, whether it be time, distance, whatever, that's going to give you the total. All right, so reading it all again, use a midpoint Riemann sum with 4 subdivisions of equal length to approximate the integral from 0 to 24 of r of t. What is the integral from 0 to 24 of r of t? R of t is our rate. So the integral from 0 to 24 is going to give us the total amount of water that flowed out of that pipe from t is equal to 0 to t is equal to 24. So that's what you would write. 258.6 gallons from 0 less than t less than 24. And you may want to actually write out 258.6 gallons from time 0 to time 24 flow out of the pipe, or something like that, in order to get full points. But how detailed you get is up to you. But that's part A. Okay, part B says, is there some time t on from 0 to 24 such that r prime of t is equal to 0? Justify your answer. And we'll be using this concept right here. This is the mean value theorem. I abbreviated it MVT. You probably all know it by that abbreviation. Okay, so is there some time t from 0 to 24 such that r prime of t is equal to 0? Okay, well, how do we know that we're going to be using the mean value theorem to figure this out? Well, let's see. It asks if there is some time between 0 and 24. And in our table, it gives us times from 0 to 24. And then it asks if there is some point on that such that the derivative is equal to 0. So it basically gives us a bunch of values for t and the value of r of t at that time. So we can calculate, we know where it starts, we see a bunch of other values, and we know where it ends. So the reason we would want to use the mean value theorem on this is because it starts and ends at 9.6. Therefore, the average rate of change of the rate itself is 0. At t is equal to 0, it's 9.6. At t is equal to 24, it's also 9.6. So the average rate of change of r of t, which is itself a rate, but don't get that confused. For the purposes of this question, we're just considering r of t some function. So the average rate of change of r of t is 0. And then it asks, is there some time t such that r prime of t, or the rate of change of r of t, is equal to 0? That's how we know we're going to use the mean value theorem. Anyway, what does the mean value theorem say? It says that if f, some function, in our case our function is r of t, is continuous on the closed interval ab. And, well, it doesn't specifically state continuity in the problem, but it says it is given by a differentiable function r. That kind of implies, it doesn't place any restrictions on that, so that kind of implies that it is differentiable everywhere. If a function is differentiable everywhere, it is continuous everywhere. So this condition is met. Our f, which is r of t, is continuous on the closed interval a to b. Our a to b, by the way, is 0 to 24. I hope you can understand why. And differentiable on the open interval a to b. Well, it states that in the problem. It's differentiable. It's differentiable everywhere, therefore it's differentiable on ab, which in our case is 0 to 24. Okay, so if f is continuous and differentiable, then, now this little backwards E symbol, I'm going to give you a little lesson in math notation. This just means there exists. That's what that means. So, if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists some c, some value c, that is an element of the open interval a to b. Now you probably won't learn about this stuff until later on in your math career, but this symbol right here just means that it is an element of. So there exists some c that is an element of the open interval a to b. Our open interval is 0 to 24. So there exists some c from 0 to 24, non-inclusive, of course, this is an open interval, such that f prime of c is equal to f of b minus f of a. Let's just plug in our values. So, there exists some c on the open interval. So we have there exists some value c. I'm sorry. There definitely exists some value c from 0 to 24 such that, and I'll just use the colon right there, that sometimes can mean such that f, well, in our case, our f is r. So such that r prime of, and what are we actually using? We're not using c, we're using t. So there exists some t on the interval 0 to 24 such that r prime of t is equal to, well, f of b. What is b? Don't forget that is our, b is actually 24. So such that f of 24 I'm sorry, this is r. Such that r of 24 minus r of 0 over 24 minus 0. Okay, so how does that help us? Well, what is r of 24? If we look at our table, it is 9.6. So we can get rid of this and say 9.6. What is r of, I'm sorry, that was r of 24, but it's also 9.6. But what is r of 0? It's 9.6. What is 9.6 minus 9.6? It's 0. So we've just showed that by the mean value theorem, there exists some time t on the interval 0 to 24 such that r prime of t is equal to 0. And that's what it asked us to show. And that is the answer and justification all rolled into one. All right. On to part C. The rate of water flow, r of t, can be approximated by q of t. And that's equal to the thing it has there, the 179th, blah, 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 blah. Use q of t to approximate the average rate of water flow during the 24-hour period. Indicate units of measure. So this is the fourth concept that we'll introduce today. The average of some function f from a to b is given by the integral from a to b of our function divided by b minus a. Okay, so, but why is that? So you know what an average is, right? If you have, a bunch of baskets, I'll just use apples, baskets of apples, and they have varying quantities of apples in those baskets. What do you do? Well, what do you do to find the total, the average number of apples in each basket? You take the total number of apples and divide it by the total number of baskets, and then you have the average number of apples per basket. This is the same idea. The average of our function f, our function is a rate of change of water flowing through a pipe. So to find the average rate of water flow, we need to find the total rate of water flow. Well, what is the total? It is the integral from our start to finish of our rate. So that would be our total represented by this. This is the integral from start to finish of f, which is our r of t. That's our rate. So this is the total right here. And then divided by the, I used in my example the number of baskets. But we're actually using the number of hours because we're trying to find an average rate at which the water flows out over a given time period. So time is our baskets and gallons of water are our apples in this case. All right. So where was I going with this? So this is the average. The average of any function f from a to b is given by the integral from a to b of our function over b minus a. So let's use that. So the average rate of water flow over our 24-hour period is going to be given by this. Our average is going to be given by the integral from start 0 to finish 24, and I got that from here. This is the total. This right here is the total of Well, it says Q of t. I'm not actually going to write out what Q of t is. It's kind of a mess. It's not that bad, but... Okay, so it's going to be equal to the integral from 0 to 24 of Q of t divided by what? B minus A. 24 minus 0. We'll put the dt in there. And then it says indicate units of measure. Okay, well, what are we talking about? What are our units of measure? We have time and gallons, and this is the average rate. So this is going to be gallons per hour. And if you actually did the integration on that Q of t, and it's not bad to do. Anybody taking or studying for this test should know how to take the definite integral in question. And what you get if you actually evaluate that integral is, or this expression, evaluate the integral and then divide it by 24, you get roughly 10.785 gallons per hour. Okay, guys, that was problem number 3. Stay tuned for problem number 4.